Hi, Honors Bio students. I'm going to show you how to do the calculations you'll need to do prior to coming to the lab on Tuesday. What you're going to investigate in the lab is what concentration of heavy metal inhibits the activity of the enzyme in spinach that breaks down hydrogen peroxide. And we're going to use copper as the heavy metal that we're going to test. We don't really know, we teachers don't really know what is the correct concentration. So we want to figure out at what point is the enzyme activity inhibited. So Ms. Little thought that at 4,000 ppm copper sulfate, most of the enzyme activity was zero, that there wasn't any breakdown of hydrogen peroxide. And so I'm not going to do that calculation because you'll want to do it, but I'm going to show you how to do the calculations with 5,000 ppm of copper sulfate, and then you can do it for the concentrations you want to use. So essentially what you're going to want to do is make up copper sulfate solutions of varying concentrations that are probably less than 4,000 ppm, and you're going to mix those in with your spinach solution and hydrogen peroxide and see which ones break down hydrogen peroxide and which ones don't. Okay, so in order to make up your copper sulfate solutions, you need to do some calculations, and that's what I'm going to show you how to do. So let's say we wanted to make 5,000 ppm of copper sulfate. The first thing you need to remember from chemistry is that 5,000 ppm is the same thing as 5,000 milligrams per liter of copper sulfate. Okay, that's a little easier units to work with. And we're going to make 100 milliliters of all of our solutions. You'll notice that this is in liters, so I don't want to mix milliliters and liters, so I'm going to take my 100 milliliters and do a quick conversion to turn it into liters. So I know 1,000 milliliters are in 1 liter, so I can cancel. And I really want to make up 1.00 liters of solution. Okay, so I'm going to take, so what I'm doing now is I'm doing the calculations to figure out how much dry copper sulfate I need to use. All right, so it's going to be like powdered copper sulfate. So I want 5,000 milligrams of copper sulfate in every liter. I want to make up 0.100 liters. So how much copper sulfate do I need? I can cancel my liters, and if I did this math, if I did this math, I would find I need 500 milligrams copper sulfate. Now, if you've been back in the labs, you'll know the balances back there don't mass out in milligrams. They mass out in grams. And so I just want to convert this 500 milligrams of copper sulfate into grams. Know that 1 gram is 1,000 milligrams. Cancel, cancel. So I find I'm going to need 0.500 grams copper sulfate. Okay, so when I mix this up, I don't say that I'm going to add this to 100 milliliters of water because that's not really correct. Instead, I say that I'm going to use 0.500 grams of copper sulfate, and I always mix my solutions with deionized water, and so I'm going to fill with DI water to 100 milliliters. Okay, so what I'm saying is that a little bit of this copper sulfate takes up some space. So if I add it to 100 milliliters of water, my solution will be slightly more than 100 milliliters. Instead, I want to add my copper sulfate and then fill up until the total volume is 100 milliliters. Okay, so this is how I make my concentrated solution. As I said before, you're going to want to make some solutions that are more dilute than this so that you can test to try to find the concentration at which the enzyme activity stops. So instead of making up a new solution every time, you're going to take this concentrated solution and you're going to dilute it down. There are some advantages to this. One is as you get very dilute, here we're massing out 0.5 gram. That's pretty easy to do. But if you make really dilute solutions, it's hard to mass out very small amounts of substance accurately. So if you dilute more concentrated solutions, you can get a better result. So let's say in this case, I want to try a 5,000 ppm solution. I also want to try one that's half as concentrated, so I want to try one that's 2500 ppm also. Okay, so I need to use my 5000 ppm solution to make this 2500 ppm solution. And in order to do that, I use a formula, a new formula. Oops. C1 V1 equals C2 V2. I don't know why I got two C's there. Okay. And in this formula, C1 is the concentration of the more concentrated solution. So in this case, that's my 5000 ppm. V1 is the volume of the more concentrated. C2 is the concentration of the solution I want to make. So in this case, that's 2500 ppm. And V2 is the volume of the solution I want to make. And I said we were going to make 100 milliliters of everything. Okay, so I know the value for this. I know the value for this. I know the value for this. V1 is what I'm trying to solve for. How much of my more concentrated solution do I use to make the new solution? So I'm going to rearrange this to solve for V1. Okay. So if I plug in my numbers, I can use milliliters here. I don't need to convert to liters in this case, but you can use liters also. So I can cancel those units, and I'll find that V1 is 50 milliliters. Okay, so in order to make a 2500 ppm copper sulfate solution from a 5000 ppm copper sulfate solution, I'm going to use 50 milliliters of the 5000 ppm solution, and then I'm going to fill with DI water to 100 milliliters total. Okay, so if I were to follow these directions, I would so far have two solutions. I'd have a 5000 ppm solution and a 2500 ppm solution, and I probably want some more dilute solutions. So for my next solution, which I'm not going to do the calculations for, I would use this 2500 ppm solution as my more concentrated solution and dilute that down to get my next lower concentration using this formula right here. Okay, that is all that you need to know before you do the lab. You're going to come to the lab knowing the recipes of all the solutions that you want to do. You're not going to want to start at 5000 ppm though, because we already know that 4000 ppm is effective. So you're going to use different concentrations probably than what I calculated here. Okay, see you Tuesday.